In this video, I want to talk about the normal equation and non-invertibility. This is a somewhat more advanced concept, but it's something that I've often been asked about, and so I want to talk about here and address it here. But this is a somewhat more advanced concept, so feel free to consider this optional material. It's a phenomenon that you may run into that's maybe somewhat useful to understand, but even if you don't understand the normal equation and linear regression, you should be able to get that to work okay. Here's the issue. For those of you that are maybe somewhat more familiar with linear algebra, what some students have asked me is, when computing this theta equals x transpose x inverse x transpose y, what if the matrix x transpose x is non-invertible? So for those of you that know a bit more linear algebra, you may know that only some matrices are invertible and some matrices do not have an inverse. We call those non-invertible matrices singular or degenerate matrices. The issue or the problem of x transpose x being non-invertible should happen pretty rarely. And in Octave, if you implement this to compute theta, it turns out that this will actually do the right thing. I'm getting a little technical now, and I don't want to go into the details, but Octave has two functions for inverting matrices. One is called pinv, and the other is called inv. And the differences between these two are somewhat technical. One's called the pseudo-inverse, one's called the inverse. But you can show mathematically that so long as you use the pinv function, then this will actually compute the value of theta that you want, even if x transpose x is non-invertible. The specific details between what is the difference between pinv and what is inv, that's somewhat advanced numerical computing concepts that I don't really want to get into. But I thought in this optional video, I'll try to give you a little bit of intuition about what it means for x transpose x to be non-invertible, for those of you that know a bit more linear algebra and might be interested. I'm not going to prove this mathematically, but if x transpose x is non-invertible, there are usually two most common causes for this. The first cause is if somehow in your learning problem you have redundant features. Concretely, if you're trying to predict housing prices, and if x1 is the size of the house in feet, in square feet, and x2 is the size of the house in square meters, then 1 meter is equal to 3.28 feet, rounded to 2 decimals. And so your two features will always satisfy the constraint that x1 equals 3.28 squared times x2. And you can show, for those of you that are, this is somewhat advanced linear algebra now, but if you're an expert in linear algebra, you can actually show that if your two features are related via a linear equation like this, then the matrix x transpose x will be non-invertible. The second thing that can cause x transpose x to be non-invertible is if you're trying to run a learning algorithm with a lot of features. Concretely, if m is less than or equal to n. For example, if you imagine that you have m equals 10 training examples, but you have n equals 100 features, then you're trying to fit a parameter vector theta, which is n plus 1 dimensional, so it's 101 dimensional. You're trying to fit 101 parameters from just 10 training examples. And this turns out to sometimes work, but to not always be a good idea, because as we'll see later, you might not have enough data if you have only 10 examples to fit 100 or 101 parameters. We'll see later in this course why this might be too little data to fit this many parameters. But commonly what we do then, if m is less than n, is to see if we can either delete some features or to use a technique called regularization, which is something that we'll talk about later in this course as well, that will kind of let you fit a lot of parameters, use a lot of features, even if you have a relatively small training set. But this regularization will be a later topic in this course. But to summarize, if ever you find that x transpose x is singular, or alternatively you find it is non-invertible, what I would recommend you do is first look at your features and see if you have redundant features like this x1, x2, being linearly dependent or being a linear function of each other like so. And if you do have redundant features, and if you just delete one of these features, you really don't need both of these features. If you just delete one of these features, that would solve your non-invertibility problem. And so I would first think through my features and check if any are redundant, and if so, then keep deleting redundant features until they're no longer redundant. And if your features are not redundant, I would check if I might have too many features, and if that's the case, I would either delete some features if I can bear to use fewer features, or else I would consider using regularization, which is this topic that we'll talk about later. So that's it for the normal equation and what it means for if the matrix X transpose X is non-invertible. But this is a problem that you should run, that hopefully you run into pretty rarely. And if you just implement it in Octave using the Pin function, which is called the pseudo-inverse function. So if you use a different linear algebra library, it's called a pseudo-inverse. But that implementation should just do the right thing, even if X transpose X is non-invertible, which should happen pretty rarely anyway, so this should not be a problem for most implementations of linear regression.